So let's get started with our second talk. So we're happy to have Haohua Deng talking about on the generalized toroidal completion of period maps.
Thank you so much, Jacob. It's my pleasure to speak here. And I will be reporting some recent results on, as the title suggests, and this is based on some works, including my joint work with Colleen Robles and Jacob. Okay, so let us get started. So what's the setup? So the setup is that if we have, suppose we have a smooth projective family over some quasi-projective base, and just so we know, like, so in the moduli theory associated with such a family, we have a integral polarized version Hall structure. Now that's the V to B. So you know that this integral polarized version Hall structure consists of a local system. That's the, fibers are the integral lattice of the certain cohomologic group of the fibers. And you also have a certain family of Hodge submodels, which we call this fiber-wisely the Hodge structure, the polarized Hodge structure on the fiber. And the interaction with the integral structure and the Hodge structure is given by the Gauss-Manning connection, and there are some Griffith transversality results. So as a consequence, if you fix the fiber, if you fix the base point here, you will get a period map. So this period map is the map from the base to the quotient of the corresponding period domain, which is the subdomain of some flat domain parameterizing or polarized Hall structures of some given type. And this gamma is the monotonic group. So in this case, we have there's a very rich literature on studying the relationship between on the geometric side and the Hodge-theoretical side. In other words, how much you can recover the information about the geometric family from its period map, or say its Hodge-theoretical information. So it is a kind of the toroidal type problems. So such problems are very widely studied in undergrad geometry moduli. And but the point is this: so for such a period map and such an integral polarized Hall structure, it is only defined on some quasi-projective base where you only have smooth fibers. But in practice, we usually have to deal with compactified modular bases, which means we have to allow some singular fibers on the boundary. So it raises the question that, can you study, so suppose this family has this modular space B has a compactification, as assume this compactification is good in the sense that the boundary devices is simple normal forcing. And in this case, can we find a way to also extend our period map to some larger space defined over B bar such that we can still recover the information about not only the smooth fibers, but also singular fibers? So this amounts to the Griffith question. The Griffith problem, I think this is from the 70s. He raised this in one of his 70s paper. That is it possible to find an extension? Let me say from this good compactification of your modular space D bar to some certain type of extension. Let me say down by the ext, such that it is an extension of your original period map. Let's say this is phi bar and phi, gamma by phi, and we have this diagram. And we are not looking for an adequate extension, so we also require that its this extension is good in the following sense. So it is first, this phi bar is Hodge-theoretically good. So means on the boundary, you can recover the limiting Hodge data are recorded. In other words, you can use this Hodge-theoretic degeneration to study the geometric degeneration. The second is that this phi bar should also be geometrically good. So in other words, because as it's well known that the original period map is a map in the category of at least a category of complex elliptic spaces. So if you add some summation like gamma is needed, you see it is a map in the category of complex manifold. And if you assume some other further conditions on D, then it is in the category of quasi-projective varieties. So we definitely require, like so this phi bar cannot be just a purely self-theoretical map. We require it is also good in the sense that this B bar to this gamma by D extend this phi bar is it also lies in some certain nice geometric category. So, for example, it is like say in the complex elliptic spaces or algebraic spaces or even projective, whatever, the best you can say. As long as it's better than the self-theoretical map. Okay? So this is Griffith's problem in the 70s. So we like say he project, like say he want to propose this program of using the full power Hodge theory to study modular problems in algebraic geometry. So what is the progress on this problem? So first, it is very well known in many classical cases. So this is well known in the classical cases. So by classical, I will like so later mean like so explain what in detail does classical cases mean. But for now, let me say the classical cases includes the moduli of curves, of course, and K3 surfaces, and like the cubic, like so surface 3 folds, 4 folds. These are very well-known modulus, well-studied modular spaces, and maybe hypercalcular varieties. And maybe like so, besides these very classical universal objects, you also can also use this method to study some special type. For example, special type Horikawa surfaces. Yeah, so there are like a lot of like so modular problems can be studied using this kind of Hodge-theoretical method, and they are all due to some classical properties if you assume them to be owned by this period domain and period map. Okay.
And in the Griffiths problem, we don't make any assumptions about the variation of Hodge structure near the boundary, huh?
Oh yeah, so like so yeah, like so we are not talking about like the Griffiths. I think the Griffiths problem is like such on the period map. So if you can extend the period map, because if you want to extend the rational Hodge structure, that amounts to some other structure like the mixed Hodge module stuff like that. But that's at least to me, it looks like some parallel, the parallel paths for like the Griffiths. I think like the focus entirely on the period map. Okay. All right. So now let me give you the most classical example. This case for Borderline of curves. So that is NG to AG. So this is well-known the toroidal maps from the modular space of genus G curve, smooth genus G curve to the modular space of rank G, principal polarized opinion varieties. So this is a toroidal map. And it maps the curve to its Jacobian, of course. So what is, and they are well-known commutations known as the Satake bilateral commutations. Let me denote it as AG, SDB, and toroidal commutations. Let me say let's associate to some certain object because this requires you to choose an extra object. Let me say sigma. So let me briefly explain what's in what are these two spaces. So as a self-theoretically, this SDB commutation is just AG itself, this joint union with all lower rank single spaces until you get a point here. Okay. And this AG sigma, this is like so for some chosen sigma, this is the blowing up this AGSDB along cusps. So as you see, this SDB communication, this boundary strata have very high co-dimension, right? So you are not compactifying by adding devices, you are adding cusps, which are very similar. So the toroidal one, if you choose nicely of the certain object, it will be a device zero communication and it will be really good, but it is not canonical. Okay, so what are the relations between these two communications and the toroidal map? So it is well known by, it is very classical result by Nakayama, I think, that this toroidal map can be extended from a map from the Mumford communication of NG bar to the SDB communication. Let me say this is phi G SDB as a regular map. And it was much later that it is by people like Alexiev or someone like so. You can also extend it to the toroidal. Let me say this is phi G sigma. And there is a natural contraction map from this toroidal to bilateral because it's a blow up, right? So this is by Nakayama, much earlier than this. This is by Alexiev. I think not expressed until the late 20th centuries. Okay. So what's the geometry meaning of these extensions? So notice that from the SDB communication, from the self-theoretical description, we can, like, so can be real that you take any C, let me say C0 from this NG bar, you take a stable curve, and you let C tilde, C0 tilde to be the normalization. So we know that this C tilde has some genus, like so, of some rank. Maybe it's lower genus. G minus K could be the same rank, but could be the same genus, but in general, like the lower genus. So in this case, this extended SVB, this toroidal map to the SVB communication, maps this C0 to exactly how you map the C0 tilde to the lower rank single space. So this is G minus K, C0 tilde. Of course, after like there are some compatibility conditions we have verified, but roughly this is the idea. Okay? So in other words, from the SDB communication, you can recover a stable curve, the information about the stable curve by recovering its normalization. But I mean, like, so the SDB communication is very coarse, so it loses a lot of information, and most of this information will be recovered in a well-chosen toroidal communication. So let me give you a geometric example. So this genus Q curve, let me say it has a single node. So this is a curve, let me say C lies in N2 bar. And its normalization is given by a smooth elliptic curve. So if this is the node, and the preimage of this node is a set of 2 points. So let's say this is E, but it is like so, a set of points. So clearly, as you see, if you map the C in N2 bar to the bilateral, it gives you the boundary point given by the Jacobian of the elliptic curve. Right? You are recovering the elliptic curve, the Jacobian of this elliptic curve. However, you are not getting any information about this P and Q. And this is recovered in the toroidal communication in the sense that in the toroidal boundary component, also in the boundary component of this AG sigma, you're able to recover both the Jacobian of your normalization, which is your elliptic curve, and the image of P minus Q inside the Picard group, 0P. And this is by the Abel-Jacobi map. So in other words, so you see, so the toroidal boundary kind of so this contraction map between from the toroidal communication to bilateral is that you are contracting those information about the Abel-Jacobi map. You only keep the smooth part. Okay, so yeah, so this is a very nice geometry example. And before we move to the next, the non-classical world, any questions or comments? All right, great. So what about the non-classical case? Because previously I'm saying so these are in the classical cases. So let me say now I'm ready to establish what's the precise meaning of classical versus non-classical. So classical now, I means if you have a moduli of certain varieties, you constantly substitute PMF to some quotient of the period domain. We call it is a classical case if this period domain D is symmetric space. In other words, so if your gamma chosen to be arithmetic, then so your period map maps into some smaller varieties. But actually, so you can check for all of these cases. This is the case, right? So for the curves, you are mapping to type 3 single domains, and similar for the cube 2, 3, 4 folds. For KT surfaces and hypercurated varieties, and also there's some special type of surfaces, we are mapping to some type 4 Hermitian symmetric domains of their quotients. So these are all classical cases. But non-classical cases, as you can see, this dominates the world of algebra geometry, right? So because most, besides these very special cases, in general, you should expect non-classical cases. Now, non-classical, literally everything else. So if you want some example, so for example, general CY3 folds or surface of general types. So if you are interested in moduli of this type of varieties, then you should not expect a story because the theory of the static bilateral communication and the toroidal communication, these are all only for locally symmetric varieties, also the classical case. So how about the non-classical case? There are some certain difficulty for finding a parallel generalization of that classical story to the non-classical case. I'll explain. So for the non-classical case, so maybe this is so a classical result. It may be if you study the parabolic geometry, that if D is a non-classical flat domain, this non-classical means it does not have a fiber structure over some Hermitian symmetric domain. Then no non-constant holomorphic functions only. So why this is important? Because if you understand the construction of the bilateral communication, you know that the algebraic construction of the bilateral communication is given by investigating the set of Ziegler modular forms. So the modular forms for Ziegler is Ziegler modular forms. Consider the gradient ring of automorphic forms, and you take the projective scheme, you get the bilateral construction. But you cannot expect any automorphic form in this case, right? There's no non-constant holomorphic functions. And partially as a result, so I think I forgot this. So who is the one making this result? But this is very classical in parabolic geometry, I guess. But the one I know who is the contributor is that in this case, if gamma is arithmetic, let me say group of D, then gamma by D has no algebraic structure compatible with the complex analytic structure of gamma by D, and this is by not too far ago by Griffith, Robles, and toroidal, I think in 40. So in other words, in the classical case, you are expecting everything can be done in the category of quasi-projective varieties. Don't even think about you can do this in the non-classical case.
So in the classical case, you mean that B is Hermitian series.
Yeah, exactly. Okay. So how to rescue this? So the rescue is that they find the generalization of the original problem. So how to rescue? Find proper generalizations. Griffith's problem. Okay.
So when you talk about these non-classical examples, are you talking about pure domain of this moduli space or?
Exactly. So if you recall, if you have a Calabi-Yau threefolds, what is the polarized construction on its middle cohomology? It has a weight 3, right? So you are considering the period domain penetrating all Hodge structures of this type, and that domain is typically, in general, not Hermitian symmetric.
For a surface of general type.
Still, right? So for surface, if it is a K3 surface or say the H20 is 1, then it is classical. But if H20 is greater than 1, then in general it is not.
Okay. Thanks.
No problem. Okay. So for the reason I explained before, it is hopeless to complete this general period map. I should use B. Okay, whatever. Can't be completed in the algebraic category. And actually, for some other reasons, it is even quite impossible to complete this in the analytic category. So even in analytic. So the question, can we find a more general category such that in this more general category, you can do this job. And of course, this more general category should also preserve some good geometry properties. But now, for now, let me ask, can we find such a category, generalizing algebraic and analytic, and still find some completion that makes our expectation? So this is the work by Kato, Nakayama, Usui. So there are a lot of works, but the work I want to emphasize here, which in my opinion is the most successful one, is the Kato, Nakayama, Usui. First by Kato and Usui, but later generalized by all of them. So what is their tools? So they are the common experts in logarithmic geometry. So they just use the logarithmic geometry to reformulate a lot of very classical results in Hodge theory. So this is the logarithmic Hodge theory. And by using this logarithmic Hodge theory, they are able to translate a lot of concepts in the classical Hodge theory into the language of log geometry. And in particular, they are able to realize a lot of things that cannot be visible in the classical cases. So let me briefly explain. Okay. So maybe before I explain the Kato-Usui theory, I have to explain one of the most classical results in Hodge theory, which is the Schmidt-Hilpern-Robles theorem. So what is the Schmidt-Newton orbit theorem? So let me choose like so maybe one of the simplest. Yeah. So first, what is the Newton orbit? So a Newton orbit is a pair, let me say sigma and F, where F is a Hodge flag, maybe genus semi-Hodge flag in the compact dual of your period domain. And sigma is a cone inside the endomorphism algebra of your rational lattice. So this V is like so the fiber of local system where you play with the period domain, generated by, so let me say this is like a convex cone generated by commuting Newton elements. Such that for any F prime inside the orbit of this F by the exponential of sigma C, because I assume like so all of its cones consist of commuting nilpotent elements. So it makes sense to talk about the exponential. So in this orbit, the pair, this rate filtration, W sigma, I will explain, F prime and sigma is a limited mixed Hall structure. So in slightly more details, this means this wave filtration, W sigma, is the Jacobson Morozov filtration, as in the serial representation theory. Of any Newton element, n in sigma. So you can probably understand as you are given any rational Newton element, n, you can always find a unique filtration such that this n acts on this filtration is graded pieces, like it has some Hodge-Lefschetz property, just like some Hodge-Lefschetz, just like so the Kato class act on the cohomological ring of a projective variety. And
should it be in the interior of sigma? Maybe?
so what?
In the interior of sigma, maybe? Or
oh yeah, interior, but like so yeah, in our literature we prefer to say sigma is open. Maybe like I say here, like it's an open convex cone.
okay.
But easier use open, you're easier to talk about the type of the mixed Hall structure, right? Okay. And then the limited mixed Hall structure means this is a mixed Hall structure, and it is graded polarized by the certain polarization form given by Q. Q is the polarization form of your original lattice. And in the second entry, you multiply by some certain power of n, depends on the weight of your graded quotient. So this is the definition of a pure linear algebraic definition of a linear mixed Hall structure. And why it is important? This is because the Schmidt-Newton orbit theorem. So that says, sorry, so Schmidt's Newton orbit theorem says that if you have a period map phi and you have a log smooth commodification, which means the boundary divisors are simple number crossing, then for any S inside S bar, there exists a unique period map, Newton orbit. Let me say sigma S, Fs, modulo gamma associated. So in other words, you can associate a gamma class of Newton orbits to every boundary point in this case. So in the case, like so you can, in the local case, if you replace S by a polydisk, then there's a uniquely determined Newton orbit at a central point. maybe like so let me just add one more action like so because it is important to know what's the action of gamma on the Newtonian orbit. So the action on the Newtonian orbit is given by you conjugate the cone by gamma and you just multiply this Fs by gamma. And okay, yeah. So let me remark what is the action of this gamma on the cone. So this provides the critical idea that what is the right approach to consider the extension problems in non-classical case. So as you see, the Simonyi orbit theorem suggests that on a boundary, the Hodge-theoretical data you have for the degeneration is given by Newtonian orbits. So it is a natural idea to how to attach all of these Newtonian orbits to the boundary, such that you can extend your original period map to a boundary. You are mapping a point to its associated Newtonian orbits. So that is the project of the Kato Nakayama study. So they construct the space of Newtonian orbits. So the construction is as below. So if you let this Kato sigma is a collection of Newtonian cones in this endomorphism algebra, we can formulate the space of Newtonian cones given by an indices containing the trivial cone 0. Then the space of Newtonian orbits, d sigma, is given by all Newtonian orbits with cone lies inside this collection. And clearly, by imposing the condition that this collection contains 0, there is a natural embedding of the original period domain into this space of Newtonian orbits, just by you mapping every element in the original period domain to the 0 Newtonian orbit. So this space of Newtonian orbit is a natural extension of your original period domain. However, this d sigma is not eventually what we want, right? We are not asking for extension of d. We are asking for the extension of d quotient by some arithmetic group or whatever, a group containing some arithmetic group. So we have to find what is the property of this space, gamma acting on this d sigma. So what are the properties of this space? So in general, actually, if you choose the sigma to be an appropriate collection of cones, then this space just behaves very nasty. However, if you assume some further compatibility conditions on the sigma, this collection sigma, then this space will have some nice properties. So let me explain. So we call sigma is a fan. Well, if in the real combinatorial sense that for any sigma and tau, you know, sigma intersect with tau is also inside this collection. And faces, any face of any cone in sigma is also lies in this collection, right? So we close on the intersection and take your faces. And it is a weak fan or weak fan if some Hodge-theoretical condition. I'm not going to spell out what is exactly here. So weak fan in some sense is slightly worse than a fan, but in the purpose of constructing that space, it is as good as a fan, but like I said, the weak fan. So the fan is determined by purely combinatorial definitions, but the definition of weak fan has a lot of relation with the Hodge-theoretic properties. Okay, so first, this collection should be a good collection. It is a fan or weak fan. Second, this collection should be compatible with gamma. Let me say gamma compatible. If, of course, the adjoint action of gamma on this collection stabilizes itself. So you take any collection, any cone in this collection, you take the conjugation, you still get the original collection. The second is that any sigma inside this cone is generated by the logarithm of some elements in this gamma. So the intuition of the second is that because in the classical case, when you consider a variation of Hodge structures on a polydisk, by the Borel's modular theorem, you know those local modular operators are quasi-unipotent. So let us assume they are unipotent. So you are going to take the logarithm of these modular operators. You got a lot of modular operators, and those are the first-hand resources for finding cones inside this collection. So you are requiring that these cones are generated by the logarithm of this in
To be sure, in
Yeah.
the Schmidt theorem,
Mhm.
that's what those cones are, right? You
Yeah.
said every stratum.
Exactly.
You just take the monotomy.
Exactly. So yeah, locally like that, those are well defined, right? If you choose something, but like globally, any choice will be determined only up to the global modular group. Any other questions or comments?
So what's the condition for the S bar extremes? I think it should be
Oh, as far as log smooth communication.
Yeah.
Of course. Yeah, any log smooth communication.
SNC. Right?
SNC, yes. All right. So with conditions on this nice space. So what is one of the main theorem in the book of Kato and Usui, Nakayama, is that if the sigma is a gamma compatible weak fan, of course fan is a weak fan, then your original period map can be extended to your SNC compatibilization B bar is phi bar to the space of this, extended space by using Newton orbits. And what is the space? What's this space? And this map and this space, both of them lies in the category of something called the logarithmic manifolds. So you can understand this log manifold, or say in general log analytic space, as a nice generalization of Euro analytic spaces. And it also has a lot of similar properties shared with Euro complex analytic spaces. So in this case, we have the following series that the image of this B bar inside this space is Morse's-on, or say the compact algebra space. Yeah, so you actually get something algebraic. Okay? So this is a nice result, but so notice that they are always assume the existence of such a gamma compatible weak fan.
This map is proper, right? The B-bar map?
Oh, of course, B bar. Yeah,
B-bar
yeah.
is compacto.
Yeah, compact, yeah. Yeah, so even if I only choose a partial communication, as long as the map is proper, the image is also compact over space. So it is nice, so that is if this is a compact over space, then that's a valuable result by Brockman theorem. But even if you replace that analytic space by a log analytic space, that's still true. So that's a very nice point that the log analytic category shared with the U analytic category. You still have the proper Brockman theorem.
Sorry, just a question. So this pure map we can define the universal cover without pushing the monotonic group, right?
The period map.
Yeah, the cover.
But your period
Universal cover of B and
you lead for the universal cover of B. Then then you have to find so you have to find a universal cover of this guy, which is also the cover of this guy, which is D, right?
Yeah.
But I don't think there's a cover of this guy. Meaningful. This D sigma doesn't have any kind of some very nice structure. Only quotient by gamma has some nice structure.
Okay.
All right. So the difficulty is that to apply the theorem, you have to construct such a thing, right? You have construct such a thing. So constructing such a sigma is the main difficulty. So there are some like a classical known result is that first, when B is a curve, suppose like so you are considered a map here defined over only a quasi-primitive curve, then the sigma is the constraint of sigma is triggered. So you just take like so the local multiple logarithms, all of those are one-dimensional rays, and you take the gamma conjugation. Clearly, this is a fact. The second is that in the classical case, like classical back to before, I mean when this D is Hermitian symmetric, as if you are familiar with the classical toroidal theory, you'll see these conditions are exactly coincide with the conditions used in Mumford Raport book. They construct toroidal modification. These are exactly those conditions. So, which means in a classical case, this K and U compactification agree with, let me use the completion. Agree with the classical toroidal modification. As long as you choose this fan to be the one used in the classical toroidal theory. However, for any other cases, very often, until recently. So maybe you can like so spot the main difficulty here, right? So when B is a curve, you have this race. So if you're conjugating one race to you have infinite many rays, right? Because you're conjugating this race by an infinite group gamma. But this race, they either intersect at the origin or they coincide. So it always satisfies the fan property. However, if you have some collection with some cones with dimension larger than 2, then you have to worry about whether these cones will intersect with each other for infinite many times. So this will terribly destroy the fan property you want. Okay? So in this direction,
Could I ask a question about why you're sort of imposing that it's invariant under the global monodromy gamma, but I mean you only need it to be invariant kind of under the local monodromy, no, right? Or is that, or I don't know, like
yeah, the point is that you are quotienting by the global monodromy group, right?
Right, yeah, but on B, like if you're at the boundary of B, couldn't you just quotient by the local monodromy and get this local extension?
Yeah, you can always get local extension. But now I'm asking for a global extension. So you have to find a way to patch all of this local extension together.
Sure.
This patching condition is given by this.
A number crossing dividers can form like loops, right? So like around the point locally you can do it, but then if you want to go around the loop of curves, you have to do it globally.
Right, yeah.
Yeah, so it's inevitable to talk about a global module. Okay, so the result is that in this direction is that in my graduate thesis 22, like so, I construct the first example. Like so, by first example, I mean the first example beyond the first two cases, known cases. So I mean the first example beyond 1 and 2. And later, in the journal with Colleen Robles in 24, we actually show that if B is a surface, so like so if B is a curve, then it is clear. But now if B is a surface, we are also be able to show that there exists an SNC completion and such a space D sigma which means you can find such a fan and you construct the corresponding Kato like the Usui space, such that your period map can be extended to this B bar to this guy. Just like so, you can just fully apply this theory when B is a surface. Okay, so this is like so we solve the surface case. However, if B has dimension greater to 3, then we expect that such an object sigma is in general does not exist. So this is due to some very annoying combinatorial reasons that actually just combinatorial reasons. Okay, so if the collection has some cones with dimension 3 or even larger, then in general do not expect you can do this. So the proof of this theory, is kind of okay. So in the first version of this paper, we give a proof, and we didn't realize that the proof actually has a gap, and until we receive our first referee report, and only after that we realized that we need a very technical finiteness result. So for those of you familiar with the fundamental paper by Becker, Klingler, and Tsimerman about the Tain topology and the definability of period map, you should be able to. You may recall the cool finiteness result is given by this. So let me let me use the one-dimensional case. So if you have a period map on a puncture disk and you lift to its universal cover, this phi tilde. Then if you check the Becker, Klingler, Tsimerman's paper, that central finiteness result, it tells you that phi z will be contained in finitely many single sets, where single sets are maybe let me say this T. These single sets are just in the Euro set single sets of the period domain D, and this T is a subset of the upper plane given by the imaginary part of Z is greater than some positive number, and the real part of Z is bounded by some other positive number. So if you in upper plane you restrict your lifted period map on some certain strip, its image is contained in finitely many single sets. Okay, so this is actually the engine of the O-minimality and scapulating Hodge theory, right? So this every definability method in Hodge theory will more or less rely on this finiteness theory. And we realized that in order to show our result, we had to show something even stronger than this. We had to show that if you deform this local period map on some certain subset, let me say in this case, let me say n, where n is the Newton logarithm, so this n is log t, and this zn is a subset in the centralizer of n, and is a fundamental set of the centralizer of n. You consider only the integral points actually. So this also contains finitely many single sets. So this is this is we didn't expect we need such a technical result, but finally we think we needed it, and we spent a lot of time to actually prove it. Okay. But anyway, so if you are interested in details of the theorem, just let me know. We can talk later. All right. Let us back to the main topic. So as I said here, for some tricky reasons, we are not expecting this the original Kato Nakayama construction is valid for the case when the base has dimension greater or equal to 3. So now let us pass to the second approach. The second approach So instead of find a completion of this full period map, so by full I mean like so you are recording the full quotient of your full period domain on the right hand side. We only consider the image. So let me say this factor here, the image of phi. Let me say this is the Weierstrass peak. We only consider find the completion of the period image. And actually, like so, we have to do some further modification because we know we can assume this period map is proper. So we can actually we need to do a state factorization, which like so this is the state factorization. So the question is, can we find a meaningful completion of this state factorization of your period map? So this is kind of also a natural generalization of the classical case, because in a classical case, the period image can be dominant, right? So like so open subset of the gamma by D can be the period image. But in the non-classical case, because of the restriction of the Griffith's transversality, the period image usually has very high condensation in your full gamma by D. So in this case, this is also a reasonable generalization of your original for the classical case of Griffith's problem. And this is the playground I play with in my joint work with Tsimerman. So let me state the main theorem here. Okay. So for any such period map, let me say I pass to the same factorization. Let's say this is phi prime. There exists SLC commodification B bar B such that, well, first, there exists a finite cover UK of B bar. So I find a finite cover of this B bar, and what we do on this finite cover is that such that on each UK there exists a local Kato Nakayama map. A local, let me say local Kato Nakayama suite map. So in this case, we are not using the original Kato Nakayama suite theory, but we're still using this theory as an intermediate step. Let me say UK to some gamma k d sigma k. Let me say this is phi k. So these are local Kato-Nakayama map. So in other words, we are not in general able to construct a global fan on the whole B, but we are still able to construct such a fan if you restrict to some certain open subset. And in this case, this phi k is proper. So in other words, like so this phi k, the image UK inside this gamma k like sigma k is analytic. Okay. So this is the first result that we can find the completion and find a finite open cover of this completion. On each member in this finite cover, we can find such an extension.
Is Zariski open or just open?
No, the analytic open. Thank you. That's a very important point. Analytic open. So these are analytic open. The second, which is even more important, is that if you consider the state factorization of each of these phi k, because they are proper, you can talk about the state factorization. This can be patched together. To a map from B to some certain, like so, let's say D prime bar. This is phi prime. This guy is our generalized toroidal compactification, which extends your original standard factorization. And in particular, this lies in the category of algebraic spaces. So it is a construction in the algebraic category.
Is UK like a neighborhood of the strata with a fixed monodromy cone or something?
In general, so it would be much more complicated. So in the best case, you can just choose this UK to be some polydisk, and the combination some polydisk, some disk, some polydisk. That's the ideal case. But in general, these UK constructions are quite some complicated. It depends on some merging condition and some local merging conditions. And in particular, you should adjust some some fancy, some nasty merging conditions like what Jacob just mentioned. So you have a loop of devices with locally you have the overlap homogenies.
But yeah, sort of, I guess I was asking whether it's like if you have multiple different strata at the boundary of B bar or something that all have the same monodromy cone, then is it sort of the union of
somehow like that. Yes, exactly.
Sort of the tubular neighborhood of union of those strata.
Yeah, exactly. Yeah, exactly. All right. So why is it this result is important? Because as you see, this completion, at least locally on this UK, they are given by this KNU completion, which means locally it records the almost the four, up to some finite, because we have the same. But up to this finite data, we recover the full toroidal boundary data, or say the Newtonian orbit boundary data. And also, it can be patched together to an algebraic construction globally, which is exactly what you are expecting from the toroidal communication, at least before you are talking about those homomorphic forms, you are also getting an algebraic construction in the original toroidal communication theory.
Is there something kind of, I was hoping to see some two domains in this Wenga thing. Is this what it looks like locally?
I won't say locally because when you say the tube domain of what, right? So whose tube domain? The data member could be very complicated and could be maybe some existing very vastly in the global basis.
That was what I was wondering. This fan, it isn't in anything, huh?
So
you have a bunch of these. You have a bunch of these cones forming a fan. They live in this much bigger space of just linear transformations of V, right?
I mean, I'm definitely not claiming that this local fan sigma k can patch to a global meaningful fan like this. I'm definitely not claiming that.
No, but even locally, do you have such thing? I mean,
locally you can.
Okay.
Yeah, because locally, when you restrict to such a UK, your merging group is highly constrained, right? But the reason why I should choose a tube domain of this the crazy stuff instead of just choose the simplest possible one is that we need the properties. If you need the properties, then you have to be very careful choosing those tube domains.
Is the gamma K just like the parabolic stabilizer of the weight filtration for that type, or?
I will say actually this gamma K has even simpler than that.
Okay.
If you're interested, we can talk that in detail. Okay. But the proof of details, for example, especially the second one is quite hard. It depends on some construction of a certain combinatorial object, which in our paper we call is a combinatorial merging complex. And that's a generalization of a fan in the classical toroidal theory and a fan in the Kato Usui theory. But anyway, so at the end of the day, you should expect the similar information on the boundary. You are encoding those Newtonian orbits. Okay, maybe 2 minutes. I just take it very briefly the applications. No one have any further questions. So applications. One application. So give a new proof of the algebraicity of Hodge psi. So as most of you know, the algebraicity of Hodge psi is firstly proved by Catalin couplet using the theory of the SL2 orbit theorem and known as simulation. And later, when the machine of O-minimality was invented, this is the direct result of the defined video pyramid. But both of these methods tells you very limited information about how this Hodge psi degenerates at the boundary, or say they intersect with the boundary. So actually, by using this machine, we are able to explicitly extend the analytic condition of being a Hodge loci to the boundary of S bar. So that gives you a much better description of what is the intersection of Hodge loci with the boundary. And the second, maybe one of the future work is that maybe like so you also know like there's another similar work generalizing the bilateral communication by vector, Lipazzi, Maury, and Tsimerman. This is the generalized bilateral communication, which we also use like so similar settings. So just like so in the classical toroidal story that you can realize a certain nice toroidal communication as a blow up of the bilateral. And so like so, hence like so you know like so in the classical toroidal case, you are able to show the toroidal communication is also lies in the projective category. Can we find a similar thing, similar generalization relating this generalized bilateral communication and this? So this is a very interesting future question. All right, so thank you for your attention.
Any other questions?
Can you say, sorry, I had just a technical question. What exactly is the group? So is it some like, I mean, you have this sort of center part, which is your monodromy cone itself, but then what else do you need to add?
Yeah, so this gamma K, actually, this is also, as you see, the cone part. But this cone need not to be exactly the homogeny cone. It could be some larger cone. So for example, if you are saying like it's a tubular neighborhood of strata with the homogeny cone sigma, this gamma K is actually sigma is gamma tau K, where tau K is a larger cone. It contains sigma, but it's a larger cone. That is what you can expect. But it's still abelian, and it still comes from the exponential of some larger homogeny cone.
But like, if you had some sort of strata that kind of, where the monodromy cone was the same and it all sort of looped around, then couldn't there be some other transformation when it loops around?
Yeah.
Like that wouldn't, but then sort of, you need to kind of patch all of them together to get a proper map, right? So
yes, so that's the main difficulty. That's why we need a like a very kind of like so the so-called combinatorial modular complex. That's a combinatorial object that makes sure that you can actually patch everything.
I see.
There
I see.
exists a B bar, right? So for
Yeah,
any B bar, it can't do it.
It exists.
I see. Yeah,
that problem.
I understand. Okay. So there exists some B bar such that kind of this problem doesn't arise and the gamma Ks are just abelian.
No, not every B bar. Okay, so if B is a surface, then this B bar can be any SNC completion of B. But if B has again like the dimension greater or equal to 3, then you have in general you have to make some really nasty, even like the not detectable. Only we know they existed, but not detectable in detail. What is the B bar you need?
But there is some B bar which is like a further SNC.
Yeah.
Block.
Exactly.
Yeah.
Questions? Okay, if not, let's thank Haohua again.